Welcome to episode 5 of this series on drawing tablet pressure. The number of pressure levels is something that comes up so often when we talk about drawing tablets. I believe you need about 2,000 levels of pressure, and this entire video is going to explain how I arrived at this conclusion. First, a few basics. This chart shows the pressure range for a hypothetical EMR pen, which goes from its initial activation force of 3 gram force to its maximum pressure of 500 gram force. To create pressure levels, this range from 0 to 500 is segmented, and each segment represents a logical pressure value. In this diagram, there are 11 logical pressure values from 0 to 10. 0, of course, means no pressure. Starting from the initial activation force, the pressure levels are evenly spaced across the physical pressure range. However, in reality, we know that EMR pens typically have a curved pressure response by default. So the pressure value segmentation really looks something more like this. Of course, you can even it out by using pressure curves, which is what we discussed in the previous episode. Now that we've related the logical pressure values to the physical pressure range, here's a quick recap of how those pressure values get translated into aspects of a stroke. First, the logical pressure values, which are numbers like 0, 1, 2, 3, etc., are normalized on a range of 0 to 1. And then a little bit of math is used to compute the width or the opacity and sometimes even the color of strokes. The vast majority of the time, people are controlling width and opacity with pressure, and that will be the focus for this episode. So we will start with how to take pressure and how it is used to affect the width of a stroke. I want to make a few clarifying points about stroke width. When we talk about stroke width, it is affected by the brush size. And you'll see me always refer to the brush size in units of pixels. You'll be seeing sizes like 100 pixels, 200, 500, and 800 pixels. These brushes tend to be large because larger brushes help us see when there are problems with pressure. And when I say brush size, I'm always talking about the maximum brush size, like the number you'd enter in Krita or Clip Studio Paint. Normalized pressure will be applied to that maximum size to yield the effective brush size at any specific point in time. So for example, if I'm pressing down at 50% pressure, 50% of an 800 pixel brush is 400 pixels. Almost every time you see a stroke in this video, you're going to see strokes that are drawn from the initial activation force all the way to the maximum physical pressure. Now, some strokes are drawn by hand. In those cases, I might not be able to hit the initial activation force because it's so tiny, but I can guarantee that I always hit the maximum pressure. And then, for all brushes used in this video, the pressure curves, whether they controlled width or opacity, they were always set to the null pressure curve. And this goes both for the driver pressure curve as well as the brush pressure curves. For the tablet, I used a Wacom Intuos Pro Medium, model number PTH660. And for drivers, I had to use multiple drivers. Some of the tests are conducted with the Wacom driver, and some of the tests are conducted with OpenTablet driver. I am considering strokes that look like this. These are typical line art strokes. I focus on these kinds of strokes with these very sharp delineated edges because they will help show when we don't have enough pressure levels. Here you see 4 red guidelines, and next to each guideline is a number. I will draw a stroke with 2, 4, 8, and then 16 pressure levels on those guidelines. I'm going to draw by putting my pen at the left edge of the red guideline and drawing all the way to the right and increasing pressure as I go along. You may be wondering how it is even possible for me to draw with fewer numbers of pressure levels. Because we know tablets today have thousands. How can I be drawing with 4? So just be a little patient. I'm going to talk about the tooling I use to accomplish this later in the video. Okay, here are the 4 strokes. Each is drawn with a brush size of 300 pixels. You may see that the ink from the strokes does not always begin at the very edge of the red guidelines. However, I was actually drawing starting from the left edge. The reason you don't see anything there is kind of just a mathematical outcome. The tooling I use causes this to happen, so you can just ignore it. It's irrelevant for this discussion. Examining the stroke with 2 pressure levels reveals how the pressure levels are segmented. The red region, where it looks like I didn't draw anything, is the 0 pressure level, so 0%. The pressure level of 1, 50%, that's the middle section. And then the pressure level of 2 is 100%, and that's the third section. And now, looking at the stroke with 4 pressure levels, you can see how this pattern expands as I have more pressure levels. So it's pretty clear. If you look at these strokes, the more pressure levels I have, the better the stroke looks. But it does raise a question. When drawing a stroke with a brush size of n pixels, how many pressure levels do I really need to draw a quality stroke? And implicitly, by answering this question, we are also understanding when more pressure levels does not help produce better looking strokes. I'm going to do 2 tests. Test number 1 is a real-world test. It produces strokes that are not perfect because they're drawn by a human hand, my hand. You can see the word replay here. I'll explain that in just a minute. Test 2 involves synthetic strokes. These are strokes that are perfectly drawn. No human could create these strokes. And the reason for that is they're not drawn by hand, they're drawn by code. We begin with test 1, the real-world strokes that are drawn by hand. First, have you ever tried to draw a pressure-sensitive stroke and then try to draw that stroke again and copy it as exactly as possible? Well, it is impossible. There is no way a human can draw a stroke and have it have the same exact position and pressure at the same moment in time as the original stroke. The fact this can't be done poses a problem for testing pressure, because every time you draw a stroke, your hand will introduce too much variation. But I solved that problem. I built my own pressure testing tool. I call it WinTab Painter because it uses the Windows WinTab API. The source code is available on GitHub if you are interested. WinTab Painter looks like a painting program, and you can draw things with it, of course, but it is actually a platform that I can use to test and explore different ideas for how I think tablets and painting programs should work. WinTab Painter has a very interesting feature, and it's going to be critical for this test. I can draw a stroke with 8,000 pressure levels, and as I draw that stroke, I can have the tool record the data packets coming from the tablet. So first, I can just replay those same data packets, and it will redraw that same exact stroke perfectly. It is mathematically equivalent to the original stroke that I drew by hand. Or, before I replay that stroke, I can change the settings. So for example, I could change the number of pressure levels that should be used. And you can see here, the stroke on the right uses 16 pressure levels, while the stroke on the left uses 8,000. And the stroke on the right definitely looks a little more rough. In test number 1, I drew only one stroke with 8,000 pressure levels. I used a brush size of 100 pixels. That's the stroke on the left. And then, in my tool, I replayed that stroke with different numbers of pressure levels from 4,000 to 16. You probably are having trouble telling the difference between all these strokes, and that's natural. Part of it is because they do look very, very similar, and part of it is probably due to just YouTube compression. However, you might be able to pick out that the 16 pressure level stroke is clearly not as attractive as the other strokes. I will dive deeper into these strokes in just a minute, but before I do, I'd like you to take a little quiz. I'm going to show you 3 strokes. One of them is the original stroke I drew by hand, and that used 8,000 pressure levels. The other 2 are simulated replay strokes. One uses 2,000 levels of pressure, and the other uses 128 levels of pressure. All you have to do is identify which stroke used which number of pressure levels. Here are the strokes. So I'll give you a few seconds, but if you need it, pause the video and see if you can tell which one is which. And up front, I will tell you, I cannot visually tell these strokes apart. Here are the answers. If you got these answers wrong, or if you got them right, I'd love to know, so please leave a comment. So let's dive deep into the strokes and see what my conclusion was. So what I will do is compare the 8K stroke to each replay stroke. So first I'll compare the original 8,000 stroke with the replay 4,000, and then I'll compare the original 8,000 stroke with the replay 2,000, etc. I asked Tablet Expert Cube to take a look at these strokes, and he was able to detect the difference at 128 pressure levels. And to me that makes sense, because the brush size is only 100 pixels, so naturally one would expect that differences would start to show up around 100 pressure levels. However, for some reason, and maybe it's because of my eyes, I had real trouble seeing quality differences in these strokes. I really noticed a degradation in quality when I got down to 32 pressure levels. I think there are some contributing factors here about why I could not see these differences so well. I'm drawing these strokes by hand, so naturally that introduces some amount of variance in pressure and in position. So that will yield a stroke which has rough edges and is not smooth. And then my WinTab Painter app has a very crude way of drawing strokes, and that is very prone to having rough edges. And at least for me, I find that these rough edges help mask quality issues. Ultimately, I would say Cube is very good at seeing differences in things like this, so I will go with his judgment over my own. And I'll say that the quality differences were noticeable at 128 pressure levels. And now I want to go a little deeper into how these comparisons between strokes were actually done. I think it's really important to spend some time on this because I want to assure you that I tried to be incredibly diligent in finding out how these strokes differed. Each time I compare the original 8K stroke versus one of the replay strokes. The first comparison is visual. This is what your eyes see. The 8K stroke is always on the top and the replay stroke is always on the bottom. I also created a diff. In this sense, what I mean by a visual diff is I subtracted one image from the other. When I do that kind of subtraction, what it means is if there's no change, I get a black pixel. And if there is a change, I get a pixel that increases towards white. So small changes are dark gray, and if it's a maximum amount of change, it's a white pixel. So on the right, you see the diffs. There are actually two. The raw diff is the black rectangle on top. But sometimes these dark gray pixels just don't show up in the raw diff. So I also created, and you can see it below the raw diff, what I call the contrast enhanced diff. In this case, any pixel which is not black will get set to white. So the contrast enhanced diff should help us see where the differences are, though of course it is quite exaggerated. But I will say honestly, even though the diffs sometimes point out differences, in many cases, I could not visually make out the difference. Okay, let's start comparing. I'm going to go through these very quickly. This is the original 8K stroke versus the replay 4000. Here is the diff. This is the original 8K stroke versus the replay 2000. Here's the diff. Here is the original 8K stroke versus the replay 1000. Here is the diff. Here is the original 8K stroke versus the replay 512. Here is the diff. Here is the original 8K stroke versus the replay 256. Here is the diff. Here is the original 8K stroke versus the replay 128. And here is the diff. Here is the original 8K stroke versus the replay 64. Here is the diff. Here is the original 8K stroke versus the replay 32. And here is the diff. Here's the original 8K stroke versus the replay 16. And here's the diff. Before we move on from test number 1, I'd like to share a few thoughts. First, I was really surprised that I had to get down to 32 levels of pressure to see quality differences from the original 8K stroke. So I am really happy that I asked Cube to review this content, because he saw differences I could not see. Second, the diffs were an interesting idea to implement. And if I do this kind of comparison again, I will definitely continue using the diffs. But to be honest, they didn't really prove as useful as I thought they would be. I thought that they would really pinpoint exactly where I should look and I'd see the differences. And they do that mathematically, but when I look at the strokes with my own eyes, I still struggle to see the differences. Moving on to test number 2, this is a test for the synthetic scenario, which is drawn not by hand, but by code. So these strokes look unnaturally perfect. I thought it was important to do a synthetic test because these kinds of strokes are so perfect, it makes it easier to see when there are differences between the strokes. In this case, I used Krita as the drawing application, and I also used OpenTablet Driver because it allows me to use a special pressure emulation plugin created by Tablet Expert Cube. This plugin offers the ability to simulate lower numbers of pressure levels. For these tests, I'm using Krita's Ink 3 G Pen brush with a size of 200 pixels and a null pressure curve. Here are all the synthetic strokes from 8,000 pressure levels down to 32 pressure levels. I noticed a subtle but clear difference in quality when I moved from 512 pressure levels to 256 pressure levels. This intuitively made sense for me because the brush width is 200 pixels, so I would sort of expect that around 256 I would see a difference. Here is the synthetic 8,000 stroke versus the synthetic 256 stroke. And here's the diff. In summary, we had two tests and they tested different types of strokes. One was real world and one was synthetic. Thinking back on what I observed, I felt a pattern emerged. When the number of pressure levels is close to the size of the brush in pixels, we start to see some visual quality issues. In other words, if you have a 100 pixel brush, you may start seeing quality issues at 100 pressure levels. And it seemed that if we used twice the number of pressure levels as the brush size in pixels, then the quality of the stroke was visually maintained. So to answer our initial question about how many pressure levels are needed for a quality stroke when the brush size is n pixels, I think the conservative answer is something like this. What this is saying is that if your brush size is n pixels, you need 2 times n pixels. But on top of it, I'm rounding up to the nearest power of 2. This formula looks like a lot of complexity to deal with, but really it's quite simple. Let's suppose you have a brush size of 7. First you multiply it by 2. This gives us 14. And 14 is not already a power of 2, so we need to round it up to the next nearest power of 2. In this case, that's 16. So to handle a stroke with a brush size of 7 pixels, I claim you need 16 pressure levels. The discussion so far has been about pressure and stroke width. But also, we have to consider opacity, or transparency is another way of expressing it. And in an image, this is expressed in the alpha channel. Here are 2 examples of how the alpha channel is used. Both of these strokes use a brush where pressure is mapped to opacity. So the harder I press, the more opaque the stroke. The stroke on the left has a sharp edge, and the stroke on the right uses a typical airbrush with a very diffuse edge. It's time for another quiz. Again, I'm going to show you 3 strokes. Each stroke is drawn by hand, but I did try to make each stroke look very similar. I used 8,000 pressure levels, then 2,000 pressure levels, then finally 16 pressure levels. I drew these strokes with Krita using the airbrush soft brush. The size of these strokes was set to 800 pixels, and the size was not affected by pressure. The only thing pressure was used for was to affect the opacity of the stroke. Keep in mind, these are real-world strokes that are drawn by hand, so there is some natural variation in how much pressure I was able to apply. As a human, I cannot apply pressure perfectly smoothly. Also, ignore how light or dark the strokes are. I drew these by hand, so sometimes I just press down harder than I intended to. What you should really be looking for is how smooth the transitions are. So again, all you have to do is identify which stroke used which number of pressure levels. Here are the 3 strokes. Again, just focus on how smooth the transitions are. I'll give you a second to think about it, but if you need to, pause the video. Here are the answers. Let me know in the comments if you were surprised by your answers to this question. To me, the stroke in the middle with 16 pressure levels was more easily identifiable. However, I could not tell the difference between the 8,000 stroke and the 2,000 stroke. And now what you're seeing is, I used Krita and OpenTablet Driver and Cube's pressure emulation plugin to draw synthetic strokes. Now in this case, pressure was not mapped to the width of the brush, but to the opacity. At 128 pressure levels, I could clearly see that the quality had degraded. There was more banding evident. So to account for opacity then, I would say the answer is really simple. You need as many pressure levels as you have levels of opacity. So for an 8-bit alpha channel, which has 256 levels of opacity, you need 256 levels of pressure. Putting this all together and accounting for both opacity and brush size leads to this formula. Again, it looks really complicated, but it's actually very easy to understand. Basically, it's saying, pick the bigger of 2 numbers. The first number is 256, and the second number is the brush size multiplied by 2 and rounded up to the nearest power of 2. It's much easier if we just graph it out like this. The x-axis is the brush size in pixels, and the y-axis is the number of pressure levels needed. As we can see, 2048 pressure levels will accommodate a brush size of 1000 pixels. And of course, that will accommodate all smaller brush sizes. So this is the origin of my statement that you only need 2000 levels of pressure, because that accounts for an 8-bit alpha channel, and it gives you quality strokes for brush sizes up to 1000 pixels. We live in a world of more is better. So why is it that I think that only 2000 is needed? First, if you're doing things like line art with sharp delineated edges, I have to ask, how many of you are really doing that with brush sizes that are bigger than 1000 pixels? What I see is that most people are drawing art with these kinds of strokes using brushes that are much, much smaller. But what about large brushes? People do use them. For example, they use brushes with complex patterns, or they use airbrushes, and those brushes can get huge. But the way those brushes work, they will mask what's happening when you're using lower numbers of pressure levels. And you saw that earlier when I used an airbrush to show you 3 different strokes, each using different pressure levels. So it's time for another quiz. I'm going to use this Krita RGBA05 Impasto Details brush and set the brush width to 500 pixels. According to my math, you'd need 1024 levels of pressure to draw a good stroke. I'll draw 3 strokes, and I'm going to use 16, 2000, and then 8000 pressure levels. See if you can identify which one is which. Okay, here are the strokes. I'll give you a moment to think about which one is which. But pause the video if you need to. So did this surprise you at all? I think it is pretty clear that, to me, all 3 strokes did a great job. Definitely the 2000 stroke and the 8000 stroke did a great job. And frankly, I think the 16 stroke also did pretty good. Again, my point is, when you use these kinds of brushes, it masks the effect of lower numbers of pressure levels. Another factor that comes into play is pressure smoothing. Pressure smoothing can compensate for lower numbers of pressure levels. Here are 3 strokes drawn in Krita with the Ink 3 G pen, using a brush size of 500 pixels. I used 8000 pressure levels for the first stroke on the left. I used 128 pressure levels for the stroke in the middle. I think you can clearly see the 128 stroke does not look as good as the 8000 stroke. But on the far right, I also drew a stroke with 128 pressure levels. But this time, I turned on pressure smoothing. Now, I am not saying this stroke looks perfect. My math says you would need to use 1000 levels of pressure for a brush this size to get a quality result. But I'm using almost a tenth of that. And with pressure smoothing, the stroke looks pretty good. Finally, instead of focusing on greater and greater numbers of pressure levels, instead, I think it's important for you to start thinking about 2 other things. First, the physical pressure range supported by your pen. If your pen has a pressure range of about 400 gram force or greater, then you'll have a much better time drawing good quality strokes with your pen. And then, of course, as I mentioned in the previous episode, learn to use pressure curves. They absolutely can help you have more control and better looking strokes. To conclude, I hope I've made a good reasoned and researched argument that 2000 pressure levels is really all you need to have a quality experience, because 2000 pressure levels will work incredibly well for the vast majority of sizes of brushes you're using and the kinds of brush you're using. If you're trying to buy a tablet, this should make your decision easy, because every tablet on the market, the vast majority, use 8000 pressure levels. Only a few have 4000. Yes, we do see tablets advertised with 16,000 pressure levels, but I just do not believe that will make a difference for the quality of your strokes. So, if you are trying to buy a tablet, please do not stress about the number of pressure levels. Every tablet in the market today is going to do a great job for you in terms of pressure levels. If you want to get picky about a tablet, instead, focus your time and energy on the physical pressure range of the pen that comes with the tablet. Thanks for your time, and I hope you enjoyed this video.